Welcome to this video. We're going to learn about the different devices we use to measure current and potential difference in a circuit. First, imagine you have a mug. The mug says, "Physics is fun," and you put water in the mug. Then you drill a hole in the bottom. What happens? The water spills out. If you drill a second hole that's much bigger, more water will spill out of that hole. On the other hand, if you put two equal-sized holes into the bottom, an equal amount of water goes through each. That's very similar to what we see with a circuit. When you connect just one resistor, you have current flowing through that one resistor. It's able to spill out of the battery just like it does through the hole. What if I take a second resistor and I connect it so that there's two pathways? And the second resistor is much easier for charge to flow through. It has a bigger area, and so the resistance is smaller. More charges can pass through, just like more water goes through the wider hole here. So there's more current exiting the battery, and when it gets to this point, it splits off. You still have the same amount of current going through the first resistor as you had before. There's more current going through this resistor because R2 is lower than R1. It joins back together. And then if you take two equal-sized resistors so that they're two separate pathways, two different pathways charge can follow, you'll have some current flowing out of the cell, and then when it gets to here it splits. And because the resistors are equal in resistance, there's just as much current going through R1 as through R2. If you block off this hole, then you still have as much water flowing through this hole. And in the same way, if you were to open a switch right here, you open the switch, then now you've blocked off current from using R2. So you still would have as much current going through R1 as before. You haven't changed its resistance. In the same way, you haven't changed how big this hole is. So you still get as much current going through R1 as before. Let's say we have a simple circuit like this, one resistor, and you want to measure the current through this resistor. You use something called an ammeter, and you break this circuit, and you put the ammeter right in there. Why do you put the ammeter here? The reason is because the ammeter tells you what the ammeter's current is. So charges come out, they flow through the wire, they all go through the ammeter, and then they all go through R1. The ammeter says 4 amps went through me, and that's the same as what went through R1. We connect the ammeter in series so that the current through the ammeter equals the current through the resistor. Let's say we have a resistor of 5 ohms. What should the ammeter's resistance be? Well, you want the ammeter to basically not disturb the existing circuit. What if the ammeter has a resistance of 5 as well? What does that do? We're going to replace this EMF with a 10-volt battery. The total potential difference is equal to the total current times the total resistance. The total potential difference is 10 because that's what the battery supplies as the EMF. We're solving for the total current. If the ammeter has 5 ohms of resistance, then the total resistance is 5 plus 5. And then the current is 1 amp. But when that ammeter is not there, all you have for the total resistance is just 5. There's no other term to add because there's no ammeter. And so the total current is 2. When you put the ammeter in place, the current drops down. Why? Because the ammeter adds additional resistance. and so less current comes out of the battery in the first place. What do we do instead? Instead of giving it a somewhat large resistance, we give it 0 ohms of resistance. That way, the ammeter doesn't contribute any resistance here to the total. Instead of adding 5 ohms, we're adding 5 plus 0. And now, the total current is 2 amps. It matches the current when there's no ammeter connected at all. To summarize, the ammeter is given no resistance so that it doesn't block current from exiting the cell. And that way, we preserve the original current before the ammeter goes in. What if you want to measure the potential difference that R1 dissipates, that it uses up? What we use is a voltmeter, and you connect a voltmeter in parallel with R1. Why do you put it in parallel? Here's the reason. The voltmeter measures the voltmeter's potential difference. So you want the voltmeter to have the same potential difference as R1. The voltmeter is placed in parallel so that it and the resistor have the same potential difference. Now let's say the resistor is 4 ohms. What should the voltmeter have as its resistance? Well, let's pretend it's the same, 4 ohms. In this case, the potential difference of the entire circuit is equal to the total current times the total resistance. 10 is the potential difference across the entire circuit. I total is unknown, and we have 2 ohms, because whenever you have 2 branches in parallel with the same resistance, the total is cut in half. That gives us a total current of 5 amps. 5 amps. Have we changed the circuit? Have we changed the circuit's current by putting this voltmeter in? Let's look and see. When there's no voltmeter, we use the same equation. We have 10 volts for the total potential difference, because that's what the EMF is, that's what the battery supplies. But now, when there's no voltmeter here, your total resistance is just 4. So the total current is 2.5 amps. We've changed it. By adding the voltmeter, we went from the original 2.5 to 5. We doubled the current. And this is actually somewhat intuitive. If you take your cup and you cut a single hole, water spills out. If you cut a second opening, then now there's 2 pathways for water to follow, and so you get twice as much water. When you create a second pathway for charges to follow, you get twice as much current, right? From 2.5 amps up to 5 amps. So how do we fix this? How do we get the current to remain at the original 2.5? How do we avoid letting more water spill out? The answer is you make that opening really, really tiny. In other words, you let just a few drops spill out. And now, the total amount of water is just about the same as it was before. What does that mean for the voltmeter? You don't want any current to go through the voltmeter. You want it to be really, really hard for current to go through the voltmeter, just like it's hard for water to spill through this hole. What makes it hard for charge to flow? High resistance. So you give the voltmeter infinite resistance, and that way, you're not really creating a second pathway, because none of the charges use that high resistance pathway. It's too hard.